Okay, so today's topic, semiconductor devices, namely bipolar junction transistor and field effect transistor, which are basic fundamental building blocks for electronics, and also this should also help you understanding how electronics works. First about the conductivity, a little bit about physics. That's a simplified model of what happens in metal. There is a metal atoms which has the outermost core, electronic core, where the electrons are. And when we are making a molecule out of atoms, basically the molecular bond happens on those core interactions. On these outer core, there are electrons, and also there are places called vacancies where the electrons can actually get stuck. And basically, the chemical bond happens when the other adjacent the metal or the atom outer core electrons are also connected to the next metal outer core, the atoms. And that makes a molecular bond, very strong bond. And however, on metals, there are more outer core electrons that are needed for making those bonds. That's why they are actually free electrons, meaning they are weakly bonded to the atoms. Fundamentally, they are bonded only by the weakest force, which is the electrostatic force between the positive, the center and the negative electron. Okay, so practically those extra electrons, free electrons in here marked as purple, they are the ones which are easily movable by external electric field, and they are the charge carriers, which means that the metals, they have excellent conductivity, which means small resistance. Okay, another small idea, thing that actually also happens, that these bonding electrons can change easily to free electrons, and also basically those they can exchange the bonds to the next ones. So practically metals are also amorphic matter, meaning easily to you can form those easily, and the melting point is rather low. Okay, that's about the physics of conductors, which are metals. And the metals have the free electrons, which are the majority of the charge carriers. Okay, semiconductors. They are not conductors, and they are not insulators either. The semiconductors overall, they are crystalline materials. So this crystal shape is more or less a must, because basically the semiconductor material has all of those vacancies filled by electrons, and they are these atoms are sharing all of their outer core electrons. Okay, which means that if there is some temperature is movement of the something practically, and in here it means that if this is in a other than absolute zero temperature, there's is regeneration and degeneration of electron hole pairs. So practically a temperature or external energy takes one of those electrons from this red circle here and moves it somewhere. So it's a free electron close by to this otherwise positive ion. Okay, so that's the semiconductor. Crystalline structure. Basically, this is possible only by the covalent bond, meaning all these outer core electrons are bonded to next atoms and shared by the neighboring atoms. Okay, and temperature is enough to generate electron hole pairs. And here, practically both electrons and holes can act as charge carriers. Charge carrier meaning a charge that can be moved by an electric field. So if you put an electric field, for example, so that it's from left to right, positive on left, then this electron likes to move towards the positive side. And well, charge is moving, meaning current is flowing. Charge carrier is moving. The same way, actually, if here's another hole is regenerating, hole pair generates, then there's a vacancy, and actually this electron can jump to the hole, existing hole, and the new hole, basically, it looks like, effectively, it looks like also holes are carrying charge, although they are tied into this geometrically they are tied, but basically it moves due to this generation and degeneration of electron hole pair. Okay, so yeah, more physics. Anyways, intrinsic semiconductors. There are basically three kinds of semiconductors, only three kinds. So bear with me. So first one is the intrinsic semiconductor, meaning it's a poor semiconductor, absolutely nothing else than just this semiconductor material. For example, here, this is a silicon, intrinsic silicon semiconductor here, only Si plus the core, the atoms, and then the electronic cores. There you have more than, say, if you have temperature or any external energy, light, heat, radiation, these small particles, anything that carries energy, if it absorbs on this matter, the energy, then it generates a electron hole pair. And more you have electron hole pairs on this matter, better the conductivity. So more energy means better conductivity, means smaller resistance. For example, this a negative temperature coefficient resistor, which is used for temperature measurement, is practically intrinsic semiconductor, a poor semiconductor. And the phenomenon behind the NTC is exactly that one. So there's a extra energy coming in form of heat, and the temperature changes. The resistance changes to smaller. Okay, great. Another one, of course, if you have seen NTC, they are usually encapsulated in a inside a copper layer, meaning that prevents light going into that NTC. material, because if you let the light absorb on this one, then you actually have a photosensor. So the conductivity of this material changes by any extra energy that comes in. Okay, and that's why it's a very good idea if you have, for example, transistors or microchips, you put those on a capsule that does not let any light inside. Or some of those are actually inside of a metallic can to prevent any other radiation sources. Okay, there's a reason for everything. That was the intrinsic, which is, well, it's a good sensor material, but not much other things into it. So actually things get pretty fancy when we start doping the semiconductor, meaning that we are doping small amounts, meaning something like 1 parts in million to 100 parts in million. Very small amount of other materials, for example, group 5A atoms, phosphorus, arsenium, or antimony, I think this SB, which has the 5 electrons on the outer core. If you put this in the silicon, single atom here and there, what happens in that the arsenium, for example, that arsenium ion on this lattice actually had the 4 of those outer core electrons are on the bond, and then you have 1 free extra electrons. So practically this extra electron is not taking or it's not used in the bonds, chemical bonds, which are very strong, but it can be easily moved by external the electric field, which means that we have extra amount of negative charge carriers, electrons. And this is called N-type semiconductor. And this is a small model of it down here. So let me put the pointer, red pointer. So we have a positive ion, that's the arsenium ion here, and the negative charge, free charge next to it. That's a simplified model of what this N-type semiconductor actually looks like. And by the way, the total charge is still 0. It's just that those negative charge carriers, they can be moved. So if you put this one on a next to a, or put a electric field, meaning that you are conducting current through this material, then these free electrons are the charge carriers, but it's still the neutral charge, the material itself. When we have this N-type semiconductor doping, we can also have P-type, which means that we have group 3A atoms like aluminum, gallium, indium, which has 3 electrons on the outer core. Those 3 electrons, if you put this one, dope a silicon, for example, with this gallium atom, actually you get 3 of these atoms are actually bonded on those. So bonded makes the chemical bond, but then you have 1 extra vacancy, meaning a hole on the lattice. And what happens there is that that hole it primarily gets filled by free electron, which means that somewhere else on this lattice there is a hole. So for example, in here, that electron, if there's an electron hole pair forming, for example, from just the room temperature, there's a plenty of generation of electron hole pairs. That electron would go here to make the bond and leaving here a hole. So practically what this one looks like, it looks like they are moving holes. The electrons like to stay on those empty vacancies, but now we have holes which are positive charge carriers. So that way we have p-type semiconductor. So we have negative n-type charge. N-type has negative charge carriers electrons, and then this p-type has positive charge carriers, namely holes. And the model, static ion, negative ion. Oops, that should be actually gallium plus, sorry. But anyways, the negative ions with a static on this lattice, and then there are these free hole positive charge carriers around. And again, this matter itself does not have any charge by itself. It's neutral in charge, equal amount of electrons and positive holes. Okay, N and P, intrinsic N and P. And we have negative charge carriers and positive charge carriers. So what's the big deal? Big deal is a p-n junction. So that's where the physics actually starts. How to make that p-n junction practically is that you will take a p-type substrate, a silicon substrate, basically a plate, 0.5 millimeter thick standard plate and 8 inches wide. 8 inches, that's 20 centimeters or diameter. And you start diffusing some n-type atoms on a high temperature and vacuum on the top of it. That basically makes you a p-n, the junction. So p-n junction is the place where this p and n actually meet. And on the close proximity, we have p-type has holes, n-type has free electrons. And on these physical forces, the bonding force, this the outer core electron vacancies, that's much higher bond than electrostatic bond. So practically that free electron from n-type travels and fills that hole. So there will be chemical bond. And which basically means if you take a look at the charge density on this matter, here the charge density would be more or less plus minus 0, because actually it has the equivalent of negative ions and positive charge carriers. Same in n-type. So in here the charge density is 0. But in here we are moving negative charges on the p-type, which means that the charge density inside of that matter is negative on the p-type and positive on the n-type. Which basically means you have an electrical field inside of that material. So practically in this you have an electrical field, internal electrical field on that junction. For the electron point of view, it looks like electrostatic potential energy, which means that if you bring an extra electron on the right hand side of this one, it likes to roll this hill and go down here. So for this from right to left, the electron flow would go easy. So, well, there's a downhill. Downhill for the electron would mean actually a voltage drop. And that's the opposite of the current flow. Okay, for the electron which comes from left to right, there's a barrier. It doesn't go above that barrier easily, which means that actually this PN junction, it works like a diode, meaning a okay, the name diode. It's a vacuum tube which conducts current only on one direction. And that's why it has anode and cathode. Cathode actually is calcium, it's potassium node, and that anode is another node, a node. Okay, I'm too old actually, so I know these kind of things, but anyways, so although that diode name comes from the tube on the era, these PN diodes, without those, you wouldn't have any cellular phones, you wouldn't have any cameras, you wouldn't have practically any electronics. Or they would weigh a ton. Okay, so pretty important piece of electronics. And okay, I was talking about how electrons flow easily from right to left, meaning that in here, that's the diode symbol. It has an arrow here showing the direction of the forward current flow, the easy way to go. Okay. And next, some applications. What kind of applications we have on the diodes? So diode is a device which allows current to flow to forward direction and blocks the current flow to reverse direction. So in that sense, it's a voltage driven switch. If the voltage on anode side is bigger than cathode, then the switch is switched on and the current flows, and on the opposite side, when the cathode voltage is higher than anode voltage, then the current flow is cut off, so it's open, or current sensing switch or voltage sensing switch. However, in reality, there is a voltage drop. If there is a current and there is a voltage drop, which actually means also power loss in diode. So there is always some power loss in these diodes. Unlike, for example, you can make pretty good capacitors and inductors are so good that for small signals you don't need to care about the power loss. But for diodes, you always have that voltage drop there. Large capacitance on reverse direction. That actually may cause capacitive coupling in high speed. So think of the picture here. This PN junction for big diodes is quite big in area. So practically this works if you have positive terminal on the cathode side. It also works as a diode, capacitor. It works also as a capacitor. And for high-speed signals, you can have capacitive coupling, not necessarily what you want, unless we are using this as a diode, as a variable capacitor. That's actually one of these applications. It's not here. There's plenty of more applications for diode than I have on this material. I'm just going through some of the most important. Leakage current, yes. It also leaks a bit. There's a small amount of current that goes through that PN junction, which means, and actually there are also some other non-idealities, but which actually just means practically that you have different diodes for different applications, just like you have different resistors, inductors, capacitors for different applications, and so on. So all the these components, but when you're going to details and start selecting components, you need to take care of in which kind of application and environment you're working. Okay, that's probably the well, this is a good place to start. Rectifier diode example. And this is the simplest form of rectifier, half-wave rectifier. And this is how it works. You have diode, D1, and here you have the load, any load. For example, this could be your mobile phone battery here, and this will be just a simple the half-wave rectifier, and whenever you have higher voltage or current flow in D1, then basically can charge your battery. And well, there's also that C1, which is a charge bank, just a capacitor. The half-wave rectifier itself is just these two parts, D1 and C1, and this is where you connect your load. There's a really nice simulation and also some other simulations of one guy, of course, on internet. So Mr. Falstad has made pretty nice simulations. So practically that what happens on if you have just this diode and resistor half-wave rectifier. The green one is a sinusoid, and then when this line goes green, it means that current is flowing, and on red, then it's the voltage is negative, and this diode actually prevents current flow. So basically, it just clips the negative cycle out. Okay, good. And that's actually what happens when you put a capacitor here. So capacitor gets charged on this cycle. When the voltage goes high, okay, here you have the capacitor is charging, until it reaches the maximum point here. Remember the capacitor and how the voltage change and current actually go hand in hand. And at that point, after the highest point, this input voltage blue actually is less than this voltage remaining in capacitor. So current doesn't flow anymore through the diode, but it actually flows from capacitor to load. So this capacitor C1 is actually as a charge bank or a battery, which gets charged on the beginning of each positive cycle, and then it works as a battery for the negative cycle or falling and the negative cycle part of this one. So what happens is that the output voltage is roughly DC. Okay, I have a small simulation also on Tinkercad. Let's see how fast is the Tinkercad today. Oh, that was okay. So I have a rectifier, halfway rectifier. Okay, come on. There we go. So I have a function generator, diode, exactly as on the previous slide. Then I have the capacitor, charge bank, and I also added a load. So my R load actually is behind of this push button. So when I push the button, then this R load is switched on. Right, there we go. So we have 50 Hertz signal. Let me turn this a little bit higher though, so it looks more interesting. Don't want to touch this here. Okay, and input is sinusoid. What happens on the up? On the output of that the rectifier. Well, I don't have any load here, so basically when the voltage reaches the maximum, which is the same as in here, I think. Yep, roughly, hard to say. Then basically the capacitor is fully charged. Let me then press the button. Okay, so it changed a lot. Let's see, somebody else probably has done. Let me to make it a little bit faster. There we go. Choice. Sorry about that. I had everything done yesterday, but it looks like I have changed something here. So pressing this one actually on this bump there, the capacitor is charged, and then that resistor and diode here is taking the charge of this capacitor, and by making this, for example, 10 microfarads instead of 100 nanofarads. Start simulation, and there we go. We get better filtering, 100 microfarads, even better. So depending on that capacitor size, you get bigger the capacitor, more charge bank you have, and better regulation you have. So less ripple. Okay, so that was the halfway rectifier, which is basically waste of circuit space, since we also have the full wave rectifier. But such for simplicity, the phenomenon can already seen on the halfway rectifier. This is nothing more than basically making this 4 diode mesh will actually give you that negative cycle also as a working cycle. Yeah, so it uses both positive and negative cycle. And if you ever get into this rectifier business, I hope not, since you are ICT engineers. We have electronics degree program for that one. But if you just happen to get into this business, forget these halfway rectifiers, use the full wave rectifier. And a power supply example. This is an actual power supply from Juho. He has all kind of stuff in his home lab. And well, in practice, if you crack this one kind of cheap old AC DC power supply open, it looks like that. It has the transformer giving for 230 it gives 12 volt AC, and after full wave rectifier and a diode, the capacitor, right size capacitor, you get something like 13.8 volts DC, with a lot of ripple if you have 650 milliamp the load on it. So this is a simulated measurement of that, how that one actually works. And this would have the RMS output voltage is 13.8. If you have a capacitor big enough for that 650 milliamp current draw, and yeah, that's how the currents are flowing to and from the resistor. Not resistor, but the capacitor blue and the resistor or this. Although that, okay, that load is a little bit off here. Anyways, so practically this happen. It works. It's just like that. If you buy cheap power supply, it's nothing more than rectifier diodes, transformer, a capacitor. And lots of noise on output. Lots of noise. All right. Another application for diodes, different diodes. Those were power diodes. So in here, the rectifier diodes actually have to be something like 1 amp diodes, because look at the currents of the IC when you start that system. So the maximum current for this the capacitor is 1 amp. So all of these diodes must withstand that 1 amp current. Okay, then we have different kind of diodes, like signal diodes, and they are optimized for signal processing, small signals, meaning say milliamp currents and few volts. For example, here the signals diodes are used to protect input port from overvoltage. This Arduino, for example, it can withstand from input voltage from minus 0.5 volts to the VCC plus 0.5 volts. So there's a half volt, the marginal, safety marginal. So with the signal diodes like that, you can actually, if you have the input voltage is something like, for example, 10 volts or so, then most of the current would go through that diode 1 to VCC. And there's only the voltage at this point would be just that diode voltage drop plus VCC. And let's see, in this case, it would probably burn this device because we have this diode forward voltage at 10 milliamp current is 1 volt, meaning at this point you have 1 volt plus VCC. Okay, there are also other diodes that can actually do the job. This diode would be too small, but they are lower voltage drop diodes. Okay, but anyways, there's also the a datasheet information about the electrical characteristics. So I just put it there for curiosity to see also the also this reverse current. So leakage current, when you have reversed voltage, how much current it actually flows through that diode, and well, those are pretty small. Even at 75 volts, higher voltage in cathode side, you have still just 5 microamps leakage current. That's not much at all. Okay, breakdown voltage, 100 volts. Okay, for small electronics, good. But breakdown voltage actually means that on that voltage, on reverse direction, it really breaks down. So it starts working with the smoke. Or actually, it always, electronics works with smoke. The trick is to keep the smoke inside of that capsule. If you let the smoke get away, then the device is done. Okay, diode has some capacitance, 4 picofarads. Doesn't sound much, but in high speed, this is a lot. Okay, and some other small things here. Light emitting diode. So we had the rectifier, some signal diodes for protecting the input, and then we have these LEDs, light emitting diodes that you have using. So that is a diode. But by some special doping, fancy doping by some silicon engineers and physicists, actually you can make a, first of all, select a transparent semiconductor, and with a special doping you can make actually so-called quantum wells, meaning for electron point of view, you have a sudden jump from one electrostatic potential level, meaning energy level, down to lower one. If you have that kind of energy change in anywhere, you get sudden energy change. It means radiation. So the energy is released as a radiation. And with high enough energy level, meaning, for example, here at 1.91 electron volts, this energy level actually translates directly into 650 nanometer wavelength red color radiation. So red color radiation coming out from that potential energy jump when electron is having downhill from here, meaning the current is flowing to forward direction. So that's why you need to put that LED, that bended terminal on the to positive and the other straight terminal to the negative when you have this this Tinkercad. So the current flows only on one direction. By the way, there are some special LEDs which has both directions and different light. So then you have an LED which have two different lights either or. So if you have been thinking, how come this small light here is either red or blue, it might be that old-fashioned. So one LED on one direction and another different color LED on another direction. Or it could be the modern ones which has several different and matrix and several wires. Anyway, so red comes from 1.90 volts electron volts energy. And higher the energy, for example, violet, 400 nanometers, requires 3.1 electron volts, meaning a jump which is equal to 1 electron dropping 3.1 volts. Okay, meaning that this voltage drop, when you have different color LEDs, the voltage drop actually depends on the color. Blue would be somewhere around 500 or 450, 500 nanometers. That's where you have about 2.7 volts electron volt their drop, which is roughly about the same as what on high power LED, white LEDs have. Speaking of which, on modern lighting applications, now we are actually replacing all the light bulbs from this incandescent light, but also the fluorescent light, old-fashioned RF fluorescent light, to the much more energy efficient white LEDs. And on white LEDs, the LED is actually blue, meaning around 450 nanometers blue colored LED, meaning about that 2.7 or 8 electron volt drop. Okay, how to make it white? You have that fluorescent material, some phosphorus material on top of the blue LED. So the blue LED actually looks like that. The white LED has this yellowish color which comes from the phosphorus material, fluorescent materials. And depending on how much you put that fluorescent material, what kind of fluorescent material you put there, you get different color spectrum. But what is really actually common in, say, most of these LEDs, white LEDs, why they are not really great spectrally, if it's just one single LED, is that it's missing some of the green. So green light, there's lacking of green light, but otherwise it's white. It's good for reading and stuff. But I have personal experience on the white LED lighting. Of course, in my home, I have been replacing the light bulbs incandescent, and those as soon as they burn, I will actually just put a LED light there. And I was trying to make a green screen. I put a green canvas behind me, and it was really green. But when I turned the artificial light on, I look at, doesn't look too green though. And then I tried that green screen on my video equipment and noticed, no, it's not green. None of my cameras are actually seeing much of green. It was more like a gray. That's because the white LED spectrum doesn't have much of green at all. Okay, so if you make a green screen, use green LEDs to light it. That's on my shopping list next. Okay, but anyways, white LED, that's how it works. For example, in your flashlight. Okay, just for curiosity and because there are some people playing with something that are not toys. I'm speaking about laser diodes. What is the difference between LED and laser diode? Okay, first of all, the initial light source is exactly the same. So this is the voltage potential drop that electron shows quantum well. Okay, however, the same thing happens as in whistle. Whistle is actually just a tuned cavity with resonant frequency. When you blow air to a resonant cavity, it starts ringing on one single frequency. Optically, you can do the same kind of cavity by making the light source in between of two mirrors. One is a 100% mirror, another one lets some of the light through it. Okay, this actually resonates the light inside. There's more physics into it, but anyways, this is one way of thinking of it. It resonates and only one frequency will come out. And not just one frequency, but it's also single phase. So meaning coherent. Coherent light with a very narrow spectrum. If you look at the power density picture here, LED of 20 milliwatts have a power density like that, quite wide spectrum. But for laser of 1 milliwatt, which is 1/20, it has much higher power density. And that power density coherence single frequency, single wavelength means that it can focus in a really small spot. And if that focus actually, if you have a good eyesight and you have white beam coming into your eye, it focuses on your retina and makes a hole guaranteed. Laser of 1 milliwatt can burn your eye permanently. So it's not a toy. So if you ever get some kids, don't let them to play with lasers. I know that there have been some incidents that people have been, showing off laser lights on helicopters, trains, buses, drivers overall. That's very dangerous business, even with those small laser pointers what you can buy from shop. So you can see the laser light only twice, one with each eye. Okay, with that warning from an old guy, a couple of other diode things like, what is the solar cell? It's a photovoltaic cell, other name for it, which is just a large area semiconductor, PN junction, meaning a diode. When the absorbing energy of light, it generates again electron hole pairs with a large area. Actually, then the internal static electric field will separate the charges, and the charges, free charges, can start, occupying so much of that material that it basically you get a charge between the P and N. And okay, so you have a charge difference between the N-type and P-type, and you can actually start collecting energy. Okay, so yeah, so what is a solar cell? It's just a diode, a very large the surface, the PN junction, nothing more than that. And okay, those are basically you can buy from a shop for a few bucks. Doesn't matter, few bucks for a decent size, which can be already used for charging the phones and such kind of things. And those are pretty efficient on turning the solar power into the electric energy. We are talking basically, even on the cheap solar cells, you can turn something like 10 to 15% of the solar energy into electric energy, which is pretty good actually. On sunny day, you can get 1 kilowatt of energy on 1 square meter, roughly. And there you get a couple of 100 watts or 100 to 200 watts of electric power. Okay, good. So solar cell, yeah, nice device. And does it actually solve our the climate crisis? I don't think so, but we will see. Image sensor. Let's get into tiny, small devices then. What is image sensor? Actually, both use photodiode matrix as light detector. What is photodiode? Well, photodiode is very small scale photovoltaic cell. It charges when you have light absorption here. And okay, there are two competing technologies, CCD, which is called charge coupled device. Practically, the charge coupled device name comes from the fact that, okay, remember this one on smaller scale, there is a charge on each of those photodiodes on this CCD camera cell. And the CCD actually use charge amplifiers. And the mechanism of transferring that charge from photocell to the charge sensitive amplifier is an analog charge transferring the matrix or line. So each line actually get transferred pixel by pixel into one the charge coupled amplifier, which actually the process takes time and requires also a high analog voltages, which is a kW of the CCD. But anyways, it uses one single charge amplifier, which is practically quite good thing, since then you can do calibrated CCD matrices. Okay. CMOS is complementary metal oxide semiconductor logic, which basically it's a switch matrix. While in CCD you take charge by charge on one single row at the time and then move into the next row. In here you can actually read each pixel separately, and this is less complex digital logic than in, or less complex the electronics actually. The digital logic is more complex, but the electronic, since it does not require that much analog amplifiers in there or analog transfers, then it's much simpler and faster. Which one is better? I don't know, and I don't really care. It's always about the specs of the final image sensor, and those specifications you can read from the device manual. If it uses CCD or CMOS, they in principle they don't have much of difference. CMOS is gaining actually the popularity. Anyhow, the color, how color sensitive is done, well, these photodiodes don't care much about what color light is absorbing, but you can actually quite easily integrate an optical filter matrix. So there are blue filters, green filters, and red filters. Usually in such a way that you have green filters more, you have a bit better sensitivity for this green color, which is the dominant color on the nature, for example, in summertime. Okay, good. So that's the image sensor. And now we can have a 5-minute break after I answer a couple of the questions on chat. There's one. Can we push the assignment deadlines to same day evening? I need to talk with you. I don't have any problem with that. I know that you have also some other courses going on, but I'm giving you a hint. I will never start looking these. I don't have any time to look at the exercise returns on the same day. So on the earliest, I will start looking at those tomorrow. And for the first exercise, it took way too long for me to start looking at those. I tried not to be hypocritical. So if I give you a deadline that I cannot keep myself, what kind of teacher I am if I'm penalizing you of not keeping a deadline that I can't keep? So practically, there's no penalty until I start assessing those exercises. So for the circuits exercises, actually, if you want to play it that way, yeah, I never take a look at those. At least on this period, I don't have any time on Wednesday evenings to start going through the exercise returns. But why we have deadlines? So basically, if you push the deadline day after day after day, I know myself that, okay, it's harder and harder to do. So if you have a strict deadline, then things get done and finished. It's part of the engineering profession. Kindly explain the grading one more time. Minimum points we need to pass this course. Minimum points I don't know yet, since we haven't got all the exercises there yet. So exercises are coming there once a week. Each exercise have 10 points, and you need 40% of the total points to pass the course. 40%. Okay, and then this third question. So deadlines are soft. Yeah, well, they're strict when I start looking at the assignments because I'm looking at those after deadline, but no penalty until that point. A couple of days only. Yeah, I know what couple of days actually mean. I have been in a working environment. A couple of days will lead into a bad situation. So this is a good and safe environment to start working on your time management, scheduling, that kind of stuff. If you have a good reason is you got a really bad flu or even worse medical conditions, of course, yeah, then we grant, but you need to explain why you need in particular the extension for the deadline. Otherwise, deadlines are what the deadlines are. Okay, good. I'm strict but fair, at least on my own opinion. Okay, so now I'm stop recording. So all of that came also to the recording, and we will have that 5-minute break.